Routh Hurwitz criterion or Routh criterion. And the case one is on the first column we have 1, 0 element, and so let me do the example first and then make a comment. So we look at this one as 5 plus 3 as 4 and 2 as 3 plus 6 as 2 plus 6s plus 9 equal to 0. So we want to apply the Routh criterion to check the stability of this systems. So here we have 1, 3, and 2, 6, 6, 9. Okay, so that is F5, 4. So we begin to apply the calculations. So basically, this first element basically is a multiplication of the two numbers multiply minus this one divided by this. Okay, so if you do this calculation, then I can write it up here. 3 multiplied by 2 minus 1 and by 6. So basically, this is 0. Okay, so that come up with a 0. So, and we can repeat calculating the remaining, that's a 3 and that's a 0. Okay, so here for this case, we have is a 0 element appearing in the first column. Okay, so that is this one. So because of this 0, if we want to continue, you can see here, here again, to proceed to the next row, basically here what we did is we're going to try to apply the same pattern and divide by this number 0, and which is infeasible. So here for this case, how can we put some fixing techniques for this? So the method is this. Here you can try is using epsilon. Because of the 0, you can try is replace these numbers by a small numbers called epsilon. So here epsilon replace this 0 by epsilon, and epsilon is small. Okay, we just treat it as a small numbers, and then we proceed. And then in the final, we get epsilon approaching to 0, then we see what happens. Okay, so now we proceed to the S2. So using the revised numbers, basically here, what we can do is this. For this number here, we're going to calculate is divided by epsilon, and then multiplication of this number minus this number. So it's epsilon and times 6 minus 3 by 3. Okay. So for that case, basically let me write it up here. This number is equal to epsilon and 6 epsilon minus 9. Okay. And then we can proceed to this number here. And for this number, again, the second number here, we can try is epsilon and then epsilon multiplied with 9 minus 3 times 0. So basically this is 9 here. Okay, so this is 0. Okay, so now we proceed to S1. So to S1, again, we can use the upper two rows, and allow me not to repeat the detailed calculations. But here you can try to check, and that number will be equal to 3 minus 2 epsilon minus 3 and 3 epsilon squared. Okay, So again, how to get this number? Simply using this as the denominator and numerator multiplication of the two numbers and minus the two numbers, and you get this one. Okay. So this one is 0. Then we go to S0 here, and that one will be equal to 9. Quickly. So keep in mind, epsilon is a small numbers, and so now we have the first column. So the first column, basically we focus on this. So here we taking by taking epsilon approaching to 0, that means bring back to the original case. So we see what happens about the sign, the change in sign of the first column. So from here we begin to calculate. So from here is no sign change. And assuming epsilon is approaching to 0 from small positive number, so from here to here is no sign change. Okay? And then from here to here, then we see what happens. When epsilon is approaching from positive to 0, basically this symbol is, if this is a normal line, okay, so this is a 0 and this is 1. So this symbol basically meaning approaching to 0 in this direction, from the positive side approaching to 0. Okay, so basically epsilon is always with here we assume it's positive. So from here, can you see how to calculate this number? Limit epsilon approaching to 0 and 6 epsilon minus 9 divided by epsilon. This one is how much? Calculate it. We can do this one here. Be careful. So basically this one is, the first term is 6 and minus 9 divided by this, right? So this one it basically is approaching to negative infinity, right? Okay, so basically from here to here, we have one sign change, okay? Basically this number is approaching to negative infinity. And from here to here, okay, now what is these numbers? And again, what is this one? The limit epsilon approaching to 0 and 3 epsilon squared and 2 epsilon minus 3. Okay, again, we can try, basically this is limit epsilon approaching to 0, and two terms. The first term is 1.5 epsilon, the second term is 3 epsilon squared, right? So basically here, each term, basically they have the epsilon there, so they're approaching to 0. And actually this term approaching to 0 faster than this one, so basically this term can be approximated by this one. Okay, so that is a positive number. Okay, so this is a negative. From here to here, it's become to positive again. So we change sign here once, we change sign here again. And from here, this is a positive, no sign change. So under this situation, we can conclude there's a two sign change. So therefore, the system is unstable. Okay. So that is the case one, and that is the summary. Basically, here is for the case one is we have 1, 0, and only 0 on the first column. Then what we did is to replace the 0 by epsilon. Then we proceed, and then we do a little simple the calculation in terms of the limit, and we can see. Okay. The second case is. Okay, I'm going to erase these portions. The second case is entire numbers become 0. Okay, so during our derivations in in some way, in certain places, the entire row becomes 0. So that is the second case. That happened. Case 2 is when entire row of the Routh table basically, this will happen in the situations is the characteristic root. The roots of the characteristic equations are complex conjugate roots. So this will happen. Such situations corresponds to the following situations. And so here I draw is the complex plane, and I try to display all the possible situations. So basically, that corresponding to is this. It has for example, it has the real roots, and one root is negative, one root is positive. Okay. So for example, this could be due to the characteristic equations containing the factors, something like this. I try to tabulate. So that is the situations. The second one is the root could be like this. So that means that is s squared plus, for example, 1. Okay. And that possible could be have this. We have the reflected. So for this case, that could be the factors like this as plus. How to make this one? I don't know how to make up this one. For example, here is s equal to positive minus 1 and plus minus. And I do this scratch calculation. You don't need to follow me. So you need to do this one. So that containing, for example, could be s minus 1 squared plus 2 and multiply with s plus 1 squared plus 2, something like this. Okay. So the characteristic equations, if we be able to factorize, then it could have the factors something like this, this and another. Okay. And it maybe also happens is we have repeated roots. Repeated roots, that means here we could have, say at this location we have the double roots here. So that means corresponding that is a square here. Okay, and for this example we could have the repeated root here. So corresponding we have a double degree here. In a similar way you can play it around, so we could have a double, so that means we have a square, something like this one, or even triple. Okay. So in graphically, if our system will be looking like this one, then for sure you will guarantee yourself when we do the Routh Hurwitz the tables, we will have the entire result zeros. So maybe we can take a look at one example here to exercise and see how to deal with this. So that is the graphical interpretation of the systems, and right now we're doing the more practical calculation of the tables. We see what happens and how to deal with the statistics. So for example, we consider the characteristic equations. Is this as 5 and plus 5 as 4 plus 11 plus 23 plus 28 and plus 12 equal to 0. Okay. So for this case, we still apply the Routh Hurwitz tables. So S5 and S4, 1, 5, 11, 23, 28, and 12. Okay, so that is a given from here. So we begin to develop. So here we do the very quick calculations. For the first number, that is 5, and 5 times 11 minus 23. So that is 55 minus 23 divided by 5, and this becomes 6.4. Okay. And for the second number here, we can do the same again. 5 and 5 multiplied with 28 and minus 1 times 12. Basically here for the second number again, multiplication of the two numbers minus the two numbers here, multiplication of the two numbers. So for this one, we can come up with is 25.6. Okay, and this one is 0. Then we, so far so good. So we proceed to S2. And let me erase the unnecessary mark here. For S2, basically here, this number is again 6.4, and then 6.4 times 23, and minus 5 times 25.6. Okay. And basically that one equal to 3. Okay, and then this number we can repeat equal to 12. So far so good. Okay. Then we proceed to S1. To S1, and again this number is calculated by 3 times 25.6 and minus 6.4 times 12. Okay, to get this number here. And to this calculation, this one becomes 0. Okay, and how about these numbers? This number basically equal to 3, the two numbers, and multiply and minus that number. Basically, this one becomes 0. Okay, right now we see the first time to show the entire row becomes 0. So that is the situations we encounter. So how to deal with this one? I want to save some space. Let me put it up a little bit here. So that is 3, 12, and S1, so that is 0, 0. So to do so, this one is here. Let me make a note. The entire row contains So that is fitting to our case 2 situations. So now we're going to try is this. We're going to replace the desired row. So let me mark it. So I'm going to replace the entire row with something such that we can proceed to our calculation. The replacement is such that we do the new row, and the terms in the new row is determined by the information above it. Okay, what I say so is this. From the information obtained from in the row above is this. We're reading is this. For this row, we call the auxiliary row and call the AS. Okay, that is the auxiliary, kind of hard to pronounce. The row that is called the AS, and AS basically is in the coefficients of 3s squared plus 12. 12 is in terms of the sequence. This is S2, S1. This is corresponding to S0. So that's 12 times S term 0 term. So basically, this is a constant term. We only write up like this. Okay. So from the row above, we obtain the auxiliary polynomial and written by this. So with this information, you simply take the dA, ds, then you obtain a 6s plus 0. Using 6s and 0 to fill up this information, this is 6, and this is 0. Okay. So with this one, we proceed our calculations. So now we have S0 here. So S0 basically obtain the first element is this. We simply using the new row, using 6 as a pivot and divide by 6. And then the number is 6 multiplied with 12 minus the 3 multiplied by 0. So this one number is 12 here. Okay. For these systems, the first one we observe is this. The first one there is no sign change in the first column. Okay, but for this special case, we still cannot make conclusions whether the system is stable or not. And then we further look into other informations. The auxiliary functions as equal to 3s squared plus 12, and has the roots as equal to positive 2j. Okay. So the which locates at, let me plot here. So this is the real s and this is the imaginary s. And the two roots actually locate is here. One is here and one is here. Okay, so that fit into our introductions and for the second case here. Okay, so this is the two roots. The two roots of these auxiliary functions, actually, there are two poles of the characteristics of the systems, okay, corresponding, we call the moduli stable Okay, the margin is stable. Basically, here, if you remember our discussions talking about the correspondence between time response and the location of the poles. And for this here, we in the time domain, the corresponding is the pure sinusoidal oscillations. Okay, so that is this case. So here we defined it. We say that is marginally stable for, due to the two roots here. Okay. So for this case, that is the situations. So for these systems, and we not only looking into the any sign change, but also we're looking from these auxiliary functions, we could get a hint about the roots. So basically, this one here, s equal to plus 2j, are part of the poles, a part of the roots of the given characteristic equations. Okay, so basically here that means if you like this one, this is the given one, that one, if you want to categorize it, basically it will at least is a square plus 4. Okay, and then remaining something we can figure out. Okay, so that is a hint we can obtain by these good functions. So actually this one we can have is, if you want to keep factorizing the things, actually you can find is s plus 1 squared, s squared plus 2s plus 1 times s plus 3. Okay, with this as a hint, that should be able very easy for us to figure out the remaining two. So actually the root is plus 2j, and for this one is yes, minus 1 and minus 1 and minus 3. Okay. So for this system, it has repeated roots here. Okay, so this pair of repeated roots. This one is we found, we do the additional work, and this work is outside the scope of the Routh Hurwitz tables. So basically these roots, repeated roots, cannot be bound by the Routh Hurwitz criterion. We need to do other additional work. Okay, so that's the comments for this.
Question.
Yes.
Can you go over again how you found the auxiliary equation?
Yes. So from this one, we proceed our calculation in building up the Routh Hurwitz tables. And for the first time, we are hit with the entire row that are containing the 0 elements. So in this way, we determine the auxiliary functions is by looking at the information above, one row above. So from here, that is 312. So basically, we come up with is 3 as square. Then the second one is we skip with 1 degree. So as square, then this one corresponding is S0.
Like every column number you skip.
Yeah, yeah. So basically here, because you see when we build up, this is S5, S3, S0. So basically the neighboring in the neighboring in one row, basically they skip of one degree. Okay, so that is the one we have this, and you like, we can maybe look at another example here and to exercise. Let me do this. So for this case, this is 1 and 2, 2, and this is S, and this is 1. Okay, so this is the simple system. So we can have 1, 1, and 2, 2, and 1, 1. Okay, so that is building up like this. So now we begin to proceed, and for this case, quickly, we hit this is 0 here. Okay. So for this case, we are with the entire row appeared in here. So basically, the one row above, that is information for us to write up the auxiliary functions. So for this case, the one corresponding is S4, the degree of 4, so that is S4. And then we skip this corresponding is 2. So 2 as second degree, and then jump 2, so from second degree to 0, so that is a constant. So that is our auxiliary functions. So from here we calculate dA, ds, and that is 4s3 plus 4s. Okay. So in this way, that is allow us to build up the new tables. The new tables. So basically, we not to use the entire row, so rather than we using this one, so that is 4 and 4. Okay, because this is 4s degree, so 4s cubed, and 0 as second, and 4s, so that is writing up like this. Okay. So now we proceed. So this is S2. So S2 will be equal to 1, 1. We can do this one quickly. Okay. Again, how come this one is 1? You simply take, this is a pivot, so 4, and then multiplication 4 times 2 minus this one, 4 times 1. So that is the reason this is 1. The same thing here, 1. Okay. And then S1 here, we can proceed similarly. So this is epsilon. So for this case, this one, we proceed to here, this is supposed to be 0. Okay. And if you do the calculation quickly, it's supposed to be 0. So that is a case, come to the situation of case 1. So because this is 0, we replace it by epsilon. So maybe here, let me use different colors. Okay, because that is 0, so we replace by epsilon. Epsilon is small. Keep that in mind. And then with the epsilon, we can proceed to the next one. So this one, basic calculation is epsilon, and is that right? So this is 0. So now for this case, calculating is epsilon, and epsilon minus 1 minus 0. How come in my note, I have a notation here, this is minus infinity. Any mistake I calculated here? maybe I have a mistake on my notes, but I trust my calculation here. So this one is supposed to be 1, right?
Doesn't it have to be 1?
Epsilon or epsilon?
Epsilon
Because
divided by epsilon.
the bottom number of every the bottom number of every column is identical.
The bottom number of, so this should be supposed to be 1. The bottom number of, say that again.
The bottom number of every column is identical.
It's identical, so that's supposed to be 1.
So looking at the bottom of the far right column, it's 1. The
Okay.
bottom of the middle
Okay.
column, it's 1. The bottom of that column should be 1.
Okay. So at least from here, for this example, from here we see there's a no sign change. Okay, there's a no sign change on the first column here. And then from here, no sign change, then at least we can begin to look for information. So from this case here, we can see this one. This one, we do the factorization. This is a square plus 1 square. Okay. So at least we want to do the factorizations. Basically, this one can be factorized as square plus 1 square containing this part. And then we can, this is a 5th degree, this is a 4th degree, and we do the calculations. So for example, here you can just divide it. Okay, so S5 plus S4 plus 2, S3 plus, say, S plus 1 divided by this one, S4 plus 0 plus 2, S squared plus 0 plus 1. You simply divide it. So this is S5 and 0 and 2 S3 and 0 plus some I screwed up.
There's no 2s squared.
2s squared, yes. Okay, so you do this one, and you can quickly come up with the other term is S plus 1. Okay, so do the hand calculation, we can factorize the system like this. So this one equal to 0, so therefore it has roots. For this simple example, the roots equal to this one, minus 1 from here. And from here, we have repeated, so that is positive minus j, and repeated positive minus j here. Okay, so for this case, we can draw the roots. So here we have repeated here, and then here we have another one minus 1 here. So for this system, at least from here we can see that is the, we still classify this as called a stable system, although we say that is the the system is unstable. Do you know the reason why? And here we have repeated roots. And let me do the Laplace transform and to show you the reason why. Let me think of my Laplace table quickly. Let me summarize. Because the characteristic equations has repeated roots, and that means the systems has repeated pause. It is unstable. And why? And let me give you reasons here. So for example, here we consider the transfer functions. And for example, let me call this a PS, okay? So the transfer functions have the characteristic equations. Basically, PS is like we did here, and whatever the QS here, we don't care. So for this particular case, we see what happens. So for PS, basically S plus 1, and then S plus square plus 1 square, 2 square, and something, this is QS, right? So here, I'm trying to give you a quantitative explanations why, when we have repeated roots on the imaginary axis, the system becomes unstable. So for this case, we can apply our the fractions and to fractorize the whole thing. So that is S plus 1, say A, and then this is S squared plus 1, and that is the B, and then we repeat it, so we have square whatever C. Okay, so I think the better way is the BS plus, I would say the B1S plus C1, and then the B1S, B2S plus C2. Okay, so we try to do the complete factorizations. By looking at this term here, for this term, we know this corresponding by the Laplace transform, that corresponding is E minus T. For this term, basically corresponding is the combination of sine and cosine. These are combinations. And we don't need to do the detailed calculation, but here the combination of sine t and cosine t, right? Because of this denominator sine squared plus 1. We know that should be come up with is in sine or cosine of the this kind of these things. Right? How about for this one? Again, so here denominator is not 1. We have exercised a lot for the two cases, and we haven't exercised for this case, and let me tabulate the situations for that case. So we have exercise is this for f of t, and the plot transform of S, so that is S plus A, so that is E minus AT, and we have exercise S squared plus A squared of A, that is sine AT. Okay, and S squared plus A squared, and S, so that is cosine AT. So that one we have done a lot. And how about this? For this one, we can check out the table is T times E minus AT. Okay. And what is this one? This one is a multiplication of the two functions. And for this one, we see that's a multiplication of two functions. Let me draw it. So this is exponentially decaying, so it is minus AT at the time. And for t, that is corresponding this time, and multiply with t, so that is 1 here. Okay, so that's a t. So we see we do the point-wise multiplication for the 2 points. We multiply together, and basically they starting from 1 here. Okay, that's starting from 0. So basically multiply from the beginning together. So once we multiply together, this one will be something like here. Okay, and multiply with this one again. We multiply with finite number with another finite number. So something somehow is here. And when time approaching to infinity, this one is decaying to 0 faster than this number going to infinity. So basically, when time goes by, say when time gets very large, basically we multiply with is a certain finite number multiply with another number. The two number, although this number on this trend approaching to infinity, but the trend of increasing the number on here is slower than the trend decreasing to 0. So we multiply the two numbers here, basically come up with a certain number approaching to 0. Somehow that speed approaching to 0 is slower than this one, but it's still approaching. So this system is still stable. Okay. And now for this case, let me try. Okay. So do we have that? I need to find the appropriate tables. In the lecture notes, I don't have that one listed. Give me time. I will try to find it. And for this case, basically this is a repeated root, and for each one, the pattern is taken on the sine cosine. Okay, and I will prove it, and the system is stable. But here I don't have that number list, so we stop here. But let me dig out my tables, and I will give you the form next time.